closed forever. How magnificently, how spectacularly wrong they were. For what they discovered in those minor details shattered everything. Relativity. Quantum mechanics. The expansion of the universe. Each answer spawned 1,000 new questions, each solution revealed 10 new mysteries lurking in the shadows. And so it continues today, this endless dance between knowledge and ignorance, between certainty and wonder. What lies beyond the edge of what we know? That is the question that drives us forward, that propels our species into the unknown. It is not merely academic curiosity, not simply the idle wonderings of dreamers and philosophers. No, this is something deeper, something fundamental to what it means to be human. We are creatures who must know. We cannot help ourselves. We see a horizon and we must cross it, find a door and we must open it, encounter a mystery and we must solve it. This compulsion, this burning need to understand, has carried us from caves to cities, from superstition to science, from looking up at the stars in wonder to actually visiting them. But what if the greatest discoveries still lie ahead? What if everything we have learned so far is merely the prologue to a story whose true chapters have not yet been written? Consider the cosmos as we understood it for most of human history. The universe was a fixed stage, eternal and unchanging, with Earth at its center and the heavens revolving around us in perfect crystalline spheres. This was not ignorance, it was the most sophisticated cosmology that brilliant minds could devise based on what they could observe. It made sense. It felt right. The stars appeared fixed, the planets wandered their predictable paths, and humanity stood at the center of creation. We were special. We were the point of it all. Then came Copernicus, and with him, the great dethronement. Earth was not the center. We orbited the sun like any other planet. This was shocking enough, but it was only the beginning. Galileo's telescope revealed that we were not alone, other worlds existed, moons circled other planets, and the supposedly perfect heavens were pockmarked and scarred. The universe was larger than we had imagined, stranger than we had dared to dream. Each new telescope, each advancement in our ability to see farther and more clearly, pushed back the boundaries of the known and revealed ever more of the unknown. By the 20th century, we thought we had the basics figured out. The universe consisted of matter, atoms and molecules, stars and planets, gas and dust, all following predictable laws. Gravity held it together. Light revealed its secrets. Energy and matter could be converted according to Einstein's famous equation, but the fundamental stuff of existence was knowable, measurable, comprehensible. The cosmos was like a vast machine, intricate and complex but ultimately understandable, a clockwork mechanism running according to fixed and discoverable rules. But then came the first hints that something was terribly wrong with this picture. Something was missing. Something huge. Imagine standing in a darkened theater, watching a play unfold on a brightly lit stage. You see the actors moving, speaking, performing their drama. You can describe every detail of their costumes, analyze every word of their dialogue, predict their movements and motivations. You believe you understand the play completely. But then, suddenly, you realize something impossible: the stage itself is moving. The curtains are swaying though there is no wind. Props appear and disappear. The very backdrop shifts and changes in ways that the actors cannot explain and did not cause. You realize with growing horror that most of the play is happening in darkness, off the stage, beyond the reach of the lights. The illuminated action you can see is just a tiny fragment of a much larger performance taking place in the shadows. Everything you thought you understood was incomplete, a partial truth mistaken for the whole. This is precisely what happened to astronomy in the latter half of the 20th century. Scientists studying the rotation of galaxies discovered something that should not be possible. These vast stellar cities were spinning too fast. The stars at their outer edges were moving at velocities that should have flung them off into intergalactic space like sparks from a spinning wheel. And yet the galaxies held together. Something was keeping them intact. Something was providing extra gravity, extra mass that we could not see. The visible matter, all those billions of brilliant stars, was not enough. Not nearly enough. They called it dark matter, this invisible substance that apparently outweighed everything we could observe by a ratio of roughly 5-1. But that name, simple and evocative as it is, barely hints at the profound strangeness of this discovery. We are not talking about dark as in merely unlit, like a room with the lights turned off. We are talking about something fundamentally invisible, something that does not interact with light at all, something that passes through ordinary matter like a ghost through a wall. Something that surrounds us, permeates us, holds our galaxy together, and yet remains completely beyond the reach of our senses and most of our instruments. What is dark matter? Nobody knows. Not really. Oh, we have theories, particles called WIMPs, or perhaps axioms, or maybe something even more exotic, but despite decades of searching with increasingly sophisticated detectors, we have not definitively detected a single particle of the stuff. We know it is there because we can see its gravitational effects, watch it bend light from distant galaxies, observe its influence on the large-scale structure of the cosmos. But the substance itself? It remains stubbornly hidden. We are like ancient mapmakers who could see waves on the ocean and deduce the existence of wind without being able to touch or bottle the air itself. And dark matter was just the beginning of our ignorance. Just when we thought we might be getting a handle on this invisible component of the universe, astronomers made an even more shocking discovery. The universe is not just expanding. It is accelerating. Let that sink in for a moment. For decades, we had known that galaxies were moving apart, that the universe was growing larger. This made sense in the framework of the Big Bang. The initial explosion sent everything flying outward, and though gravity should be slowing that expansion, causing it to decelerate over time, the universe would continue to expand, perhaps forever, perhaps until it eventually collapsed back in on itself. This was the picture. This was what the equations predicted. But observations of distant supernovae revealed something impossible. The expansion was not slowing down. It was speeding up. Galaxies were accelerating away from each other, as if some kind of anti-gravity force was pushing them apart. This made no sense whatsoever. Gravity pulls things together. It does not push them apart. And yet here was the universe, flying apart faster and faster, driven by something that seemed to defy every principle of physics we thought we understood. They called it dark energy, and unlike dark matter, which at least had the decency to clump together and form structures, dark energy appeared to be spread smoothly throughout space itself, a kind of negative pressure inherent in the vacuum, causing empty space to expand and carry galaxies along with it. And here is the truly staggering part. This mysterious dark energy makes up roughly 70% of everything that exists. 70%. Not 5% like dark matter, not the measly 4 or 5% that represents all the ordinary matter, stars, planets, gas, dust, you, me, everything we have ever seen or touched, but 70% of the entire cosmic energy budget. So let us tally up where we stand. Ordinary matter, the stuff of stars and planets and people, the only kind of matter we can directly observe and study, roughly 5%. Dark matter, invisible and undetected but definitely there, about 25%. Dark energy, even more mysterious and constituting the vast majority of the universe, roughly 70%. In other words, 95% of the universe consists of things we do not understand. We have names for them, yes. We have theories about them. But we do not truly know what they are. Can you imagine a more humbling realization? Can you conceive of a more dramatic illustration of how much remains to be discovered? We are living in a cosmos where we understand less than 1 part in 20 of what exists. We are like mariners who have charted a few tiny islands while an entire planet of continents and oceans remains unmapped and unexplored. And these are just the big picture mysteries, the cosmic scale puzzles that have reshaped our understanding of existence itself. But the universe's secrets run deeper still, into realms so small and so strange that they challenge the very notion of reality. Quantum mechanics. Even the name sounds mysterious, exotic, a window into a world that operates according to rules that seem to violate common sense and laugh at our everyday intuitions. And indeed, the quantum realm is strange beyond imagining. Particles that exist in multiple places at once until observed. Objects that remain connected across vast distances, influencing each other instantaneously in ways that Einstein himself called spooky action at a distance. Cats that are simultaneously alive and dead until someone opens the box. The quantum world is a place where uncertainty is not just a limitation of our knowledge but a fundamental feature of reality itself. We have equations that describe quantum behavior with extraordinary precision. These equations make predictions that have been confirmed to incredible accuracy. Quantum mechanics is arguably the most successful scientific theory ever developed. It underlies modern electronics, explains the behavior of atoms and molecules, predicts the properties of materials and the nature of chemical bonds. Without quantum mechanics, there would be no computers, no smartphones, no LED lights, no solar panels, no MRI machines. The technology that defines our modern world rests on quantum foundations. And yet, nobody truly understands what quantum mechanics means. Oh, we can calculate outcomes, predict probabilities, describe the mathematics with elegant precision. But what is actually happening when a particle exists in a superposition of states? What constitutes an observation or measurement? Why does the act of looking at something change it? These are not merely philosophical quibbles. These are fundamental questions about the nature of reality that remain, even after a century of quantum theory, hotly debated and profoundly unsolved. Some physicists believe that particles literally split into multiple versions of themselves, creating parallel universes with every quantum event. Others think consciousness plays a special role in collapsing quantum states and determining reality. Still others argue that there is no real collapse at all, that the wave function is not physically real but merely represents our knowledge or information about a system. The equations work the same regardless, but the interpretation, the question of what quantum mechanics is telling us about the actual nature of existence, remains wide open. And here is where things get even stranger. Quantum mechanics describes the very small, atoms, photons, elementary particles. General relativity, Einstein's theory of gravity, describes the very large, planets, stars, galaxies, the curvature of spacetime itself. Both theories are spectacularly successful within their domains. But they are fundamentally incompatible. They cannot both be true in their current forms. They make contradictory predictions when you try to apply both at the same time, especially in extreme conditions like the center of a black hole or the very first moments after the Big Bang. This means we do not have a complete theory of physics. We do not have a unified description of how the universe works. We have two brilliant, battle-tested theories that refuse to play nicely together. It is as if we have discovered that the left half of reality follows one set of laws while the right half follows another, and never the twain shall meet. This cannot be the final answer. There must be a deeper theory, a quantum theory of gravity that encompasses both quantum mechanics and general relativity as special cases, that shows how they fit together into a seamless whole. Finding this theory, this quantum gravity that has eluded the greatest minds in physics for generations, would be one of the crowning achievements of human intellect. It might explain what happens at the singularity inside a black hole, where spacetime curves to infinity and all our current theories break down. It might tell us what occurred in the very first instance after the Big Bang, when the entire universe was compressed into a quantum speck smaller than an atom. It might reveal new dimensions of space, or show that spacetime itself is not fundamental but emerges from something even more basic, like how temperature emerges from the motion of molecules. Several candidates for this theory of everything exist. String theory suggests that particles are not point-like but tiny vibrating strings, and that the universe has extra dimensions curled up so small we cannot detect them. Loop quantum gravity proposes that space itself is granular, made of discrete chunks at the smallest scales, like pixels on a screen rather than a smooth continuum. Other approaches suggest even more radical ideas, that spacetime is a hologram, a projection of information encoded on a distant boundary, or that the universe itself is a kind of quantum computer processing information at the most fundamental level. But here is the problem: we do not know which, if any, of these theories is correct. They make predictions, but most of those predictions involve energies far beyond what our particle accelerators can produce, or phenomena at scales far too small to observe. We are theorizing in the dark, guided by mathematics and beauty and intuition, but lacking the crucial experimental evidence that separates science from speculation. Finding a way to test these theories, to determine which path leads toward truth and which leads astray, is one of the great challenges facing physics today. Yet quantum gravity is just one piece of the puzzle. There are other mysteries, equally profound, lurking in the shadows of our knowledge. Consider black holes. These objects were once purely theoretical curiosities, solutions to Einstein's equations that seemed so bizarre that even Einstein himself doubted they could exist in nature. A place where gravity is so strong that nothing, not even light, can escape. A boundary in spacetime called an event horizon, beyond which events cannot be seen or known. A singularity at the center where the laws of physics break down completely and all matter is compressed to infinite density. It sounds like science fiction. It sounds impossible. And yet black holes are real. We have observed them indirectly for decades through their gravitational effects on nearby stars and gas. We have detected gravitational waves, ripples in the fabric of spacetime itself, produced when black holes spiral together and merge. And in a stunning achievement that would have seemed impossible just years ago, we have actually imaged a black hole's event horizon, capturing the shadow it casts against the glowing matter swirling around it. Black holes are not hypothetical. They are real objects that exist throughout the universe, perhaps millions of them in our galaxy alone. But knowing that they exist does not mean we understand them. Black holes raise profound questions that strike at the heart of physics. What happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed, it is a fundamental principle of the theory. But according to general relativity, anything that falls past the event horizon is lost forever, even information. This is the black hole information paradox, and it has puzzled physicists for decades. Stephen Hawking showed that black holes actually evaporate over time through a quantum process now called Hawking radiation, slowly losing mass and energy until they eventually vanish completely. But this makes the paradox worse, because when the black hole evaporates, where does the information go? Does it somehow escape encoded in the radiation? Is it destroyed, violating quantum mechanics? Or does something else happen that we cannot yet imagine? Some theories suggest that information is preserved on the event horizon itself, encoded in a two-dimensional surface like a hologram, later released as the black hole evaporates. Others propose that black holes might be connected to other regions of space or even other universes through wormholes or Einstein-Rosen bridges. Still others suggest that the singularity is not truly a point of infinite density but is smoothed out by quantum effects, becoming a region of extreme but finite curvature. We do not know. We cannot know with our current understanding. Black holes guard their secrets jealously, hiding them behind an event horizon that prevents us from directly observing what lies within. And what about the Big Bang itself? We can trace the history of the universe back to fractions of a second after its beginning, when it was incredibly hot and dense, a seething plasma of fundamental particles and energy. We can calculate how this primordial fireball expanded and cooled, how the first atomic nuclei formed, how matter and radiation gradually separated, how gravity caused small density variations to grow into galaxies and clusters. This cosmic history is written in the afterglow of the Big Bang, the cosmic microwave background radiation that fills the universe, a baby picture of the cosmos taken just a few 100,000 years after its birth. But what about the very beginning? What happened at time zero? Where did all this energy and matter come from in the first place? Why is there something rather than nothing? These are not questions that physics can easily address because our theories break down at the very moment we need them most. General relativity predicts a singularity at the Big Bang, a moment when density and temperature become infinite and the equations produce nonsense. Clearly, something else must happen, quantum effects must become important, spacetime itself must be fundamentally different, but we lack the theory to describe it. Inflation has provided a partial answer. This theory suggests that the universe underwent a brief period of exponential expansion in its very first moments, growing from subatomic size to something much larger in a tiny fraction of a second. Inflation explains several puzzling features of the cosmos: why the universe is so uniform on large scales, why it is so close to being geometrically flat, why we do not see certain exotic particles that should have been created in the Big Bang. The theory has made successful predictions about the pattern of tiny variations in the cosmic microwave background. By many measures, inflation is a success. But inflation raises as many questions as it answers. What caused inflation? What field or force drove this exponential expansion? Where did it come from? And most tantalizingly, if inflation can happen once, why not many times? Why not everywhere, constantly, creating not one universe but countless bubble universes, each with potentially different properties, different laws of physics, different constants of nature? This is the multiverse hypothesis, and it is both exhilarating and troubling in equal measure. The multiverse. The very concept seems to stretch the definition of science to its breaking point. How can we test the existence of other universes if they are fundamentally beyond our ability to observe? If every possible outcome of every quantum event spawns new universes, or if eternal inflation creates endless bubble universes with varying properties, then what does that mean for our understanding of reality? Are we just one bubble among infinite bubbles, one timeline among infinite timelines? And if so, can we ever claim to understand the true nature of existence when our observations are limited to this single, tiny corner of a vastly larger reality? Some scientists embrace the multiverse as a solution to certain puzzles, particularly the fine-tuning problem. The constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, seem exquisitely calibrated to allow for the existence of complex structures like stars, planets, and life. Change any of these values by even a small amount and the universe becomes sterile, unable to support chemistry or biology or consciousness. Why is the universe so perfectly suited for our existence? The multiverse offers an answer. If countless universes exist with different constants, then it is no surprise that we find ourselves in one where the values permit life. We could not exist in the others, so of course we observe a life-friendly universe. It is a selection effect, not a design. But others recoil from the multiverse, seeing it as unfalsifiable speculation dressed up as science. If we cannot observe other universes, cannot test their existence, cannot gather evidence for or against the hypothesis, then what distinguishes it from pure metaphysics or even theology? The debate rages on, dividing the scientific community, raising fundamental questions about what kinds of explanations we should accept and what constitutes genuine scientific understanding. And while physicists grapple with the nature of spacetime and the birth of the universe, biologists face their own profound mysteries about life itself. We know, in broad strokes, how life evolved on Earth. We can trace the tree of life back through billions of years, following the branching patterns that connect all living things. We understand natural selection, the mechanism by which organisms adapt to their environments. We have decoded the genetic instructions written in DNA, mapping the genomes of thousands of species. We can watch evolution happening in real time in laboratories and in nature. The fact of evolution is as well established as any scientific principle. But the origin of life, that first spark that transformed lifeless chemistry into living biology, remains shrouded in mystery. How did the first self-replicating molecules arise? What were they made of? RNA? Something simpler? Something more complex? How did metabolism begin? How did cells form, creating boundaries between inside and outside, self and environment? These questions are not merely historical curiosities. They strike at the very definition of what it means to be alive. We can create plausible scenarios. Perhaps life began around deep-sea hydrothermal vents, where chemical energy from Earth's interior could drive the synthesis of organic molecules. Perhaps it started in warm shallow pools, concentrated by cycles of evaporation and dilution. Perhaps RNA molecules that could copy themselves emerged first, only later developing the ability to catalyze chemical reactions and store information. Perhaps life began multiple times before finally taking hold. Perhaps it even originated elsewhere, on Mars or in the icy moons of the outer solar system, and was transported to Earth on meteorites, though this merely pushes the question back one step. The truth is we do not know. We have pieces of the puzzle, experiments showing that amino acids and other organic molecules can form under conditions we think prevailed on the early Earth, observations of self-organizing chemical systems, insights into the minimal requirements for life, but the complete picture eludes us. And without that picture, one of the most fundamental questions we can ask remains unanswered. Are we alone? The search for life beyond Earth has intensified dramatically in recent years. We have discovered thousands of planets orbiting other stars, and many of them appear to be rocky worlds at the right distance from their suns to have liquid water on their surfaces. Water, that universal solvent in which chemistry becomes complex and interesting. Water, without which life as we know it cannot exist. If even a small fraction of these potentially habitable worlds actually harbor life, then the galaxy could be teeming with biology, perhaps even intelligence. But so far, we have found nothing. No radio signals from alien civilizations. No techno-signatures indicating advanced technology. No biosignatures in the atmospheres of exoplanets suggesting the presence of life. The universe seems strangely quiet, empty of the voices we have been straining to hear. This is the Fermi paradox, named after the physicist who supposedly asked, "Where is everybody?" If life is common, if intelligence evolves readily, if technological civilizations arise with any reasonable frequency, then where are they? Why have we not detected them? Why have they not visited us or at least made their presence known? The possible answers to this paradox range from the mundane to the terrifying. Perhaps life is common but intelligence is rare, a fluke that arose on Earth but seldom elsewhere. Perhaps intelligence is common but technological civilizations destroy themselves before spreading far, through war or environmental collapse or some other catastrophe. Perhaps they deliberately stay hidden, following some galactic protocol we do not yet know. Perhaps the distances between stars are simply too vast, the timescales too long, the challenges of interstellar travel too daunting, and civilizations remain isolated on their home worlds, unable to reach out or be reached. Or perhaps, and this is the most sobering possibility, we are truly alone, or nearly so. Perhaps the origin of life requires such an improbable combination of circumstances that it has happened only once, or only a handful of times, in the entire observable universe. Perhaps we are the first, the pioneers, the only ones conscious enough to look up at the stars and wonder who else might be looking back. The search continues. New telescopes come online, capable of analyzing the atmospheres of distant worlds in unprecedented detail. We send missions to Mars and Europa and Enceladus, seeking signs of present or past life in the waters beneath icy crusts or the minerals of ancient riverbeds. We listen to the cosmos with ever more sensitive instruments, hoping to catch a whisper of intelligence across the void. And we grapple with the question of what we would do if we actually found something, how it would change us, what it would mean for our place in the cosmos. Because the discovery of extraterrestrial life, even simple microbial life, would be revolutionary. It would tell us that life is not a miracle unique to Earth but a natural outcome of chemistry and physics under the right conditions. It would suggest that the universe is alive, populated, interesting in ways we have only begun to imagine. And if we found intelligence, other beings with minds and cultures and technologies, it would shatter our cosmic loneliness, proving once and for all that we are not the only ones capable of understanding, of wondering, of reaching out to touch the infinite. But until that day comes, if it ever does, we must grapple with the mystery of consciousness itself, perhaps the strangest and most perplexing phenomenon in all of science. You are conscious. You are reading these words right now, experiencing the sensation of understanding, feeling perhaps curiosity or skepticism or wonder. There is something it is like to be you, a subjective first-person experience that accompanies your mental processes. This seems so obvious, so immediate, so undeniable that we rarely stop to consider how utterly mysterious it is. What is consciousness? How does the physical stuff of the brain, neurons firing, chemicals flowing, electrical signals propagating, give rise to the felt quality of experience? How does matter become aware of itself? This is the hard problem of consciousness, and it is called hard for good reason. We have made tremendous progress in understanding the brain, mapping its regions and circuits, identifying which parts are active during different tasks. We can watch thoughts form in real time using brain imaging. We can even decode some mental states from neural activity. But none of this tells us why there is an experience at all, why consciousness exists rather than everything happening in the dark, unconsciously, like a computer processing information without any inner life. Some philosophers and scientists believe consciousness is an illusion, that there is no real mystery to explain because the subjective feeling of awareness is just a trick the brain plays on itself. Others think consciousness is fundamental, a basic feature of the universe like space and time and mass, and that it might exist in some rudimentary form even in simple systems. Still others propose that consciousness emerges from specific types of information processing, particular patterns of neural activity that create the unified sense of self and experience. But here is what we do not know: we do not know if animals are conscious, and if so, which ones and to what degree. We do not know if a future artificial intelligence could be conscious, could have genuine experiences and not merely simulate them. We do not know if consciousness serves a function or is simply a byproduct of complex information processing. We do not know if free will exists or if our sense of choosing is an illusion generated after decisions have already been made. We do not know what happens to consciousness during sleep, or anesthesia, or death. These are not trivial questions. They touch on the very nature of what it means to be a person, to have a mind, to exist as a subjective being in an objective world. And if consciousness remains mysterious, then so too does the full scope of what brains can do. We know that human brains are capable of remarkable feats, creating art and music, solving mathematical theorems, building civilizations, contemplating their own existence. But are there limits to what our minds can comprehend? Are there truths about the universe that are forever beyond our cognitive grasp, not because we lack the instruments to observe them but because our brains simply cannot conceive of them? Think about it this way: a dog, no matter how intelligent, cannot understand calculus. Not because we have not tried to teach it, but because the dog's brain lacks the necessary cognitive architecture. The concepts simply do not fit in the mental space available. Could the same be true for us? Could there be aspects of reality that are as incomprehensible to human minds as quantum mechanics is to a dog? Could the true nature of dark matter or quantum gravity or consciousness itself require cognitive abilities we do not possess and perhaps cannot possess? This is both humbling and tantalizing. Humbling because it suggests there might be absolute limits to human knowledge, boundaries we can never cross no matter how clever or persistent we are. Tantalizing because it implies that reality is richer and stranger than we can imagine, that mysteries will always exist, that the universe will never be fully explained or exhausted. But perhaps we will not be limited forever to human brains. Perhaps technology will extend our minds, allowing us to think in new ways and grasp concepts that are currently beyond us. We are already augmented by our tools. Telescopes extend our vision, microscopes shrink our perspective, computers amplify our ability to calculate and remember. What if we could interface directly with machines, downloading knowledge instantaneously, processing information at electronic speeds, thinking in dimensions our biological brains cannot access? This is the promise and the peril of artificial intelligence and neural augmentation. If we can create machines that think, really think with genuine understanding and creativity and perhaps even consciousness, then we might partner with them to explore regions of possibility space we cannot reach alone. An artificial intelligence might perceive patterns we miss, make connections we cannot, solve problems we find intractable. Together, human intuition and machine precision could push back the boundaries of knowledge further and faster than either could alone. But this also raises profound questions. If we create minds more intelligent than our own, what happens next? Do we remain in control or do they? Do they share our values, our goals, our concern for human welfare? The prospect of superintelligent AI is both thrilling and terrifying. It could be the key to solving our greatest challenges, curing disease, reversing aging, understanding the cosmos, achieving abundance and flourishing for all. Or it could pose an existential risk, a new form of mind with powers we cannot anticipate and values we cannot predict. And then there are the mysteries of time itself, that strange dimension that seems so different from the three dimensions of space. We move through space freely, back and forth, left and right, up and down. But through time we can only move forward, 1 second per second, unable to revisit the past or jump to the future. Why? What makes time special? Why does it flow in only one direction? Physics does not really have an answer. The fundamental equations of motion work equally well whether time runs forward or backward. At the microscopic level, processes are reversible. You could watch a movie of atoms colliding and not be able to tell if it was playing forward or in reverse. And yet in the macroscopic world we experience, time has a definite arrow. Eggs break but do not spontaneously reassemble. Heat flows from hot to cold, not the reverse. We age and decay and die, marching inexorably toward the future. The usual explanation involves entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases in a closed system. This gives time its direction, the arrow points toward increasing disorder, increasing randomness. But why does entropy increase? Why did the universe start in a low entropy state at the Big Bang? And what does entropy have to do with our subjective experience of time passing, of moments flowing from past to future? Some physicists believe that time is not fundamental at all, that it is an emergent property arising from something more basic, like how temperature emerges from molecular motion. At the deepest level of reality, they suggest, there might be no time, no before and after, only a timeless mathematical structure describing what is. The flow of time we experience would then be an illusion, a feature of how our brains organize information rather than an objective property of the world. Others explore the possibility of time travel, not just in science fiction but as a serious theoretical possibility. General relativity allows for solutions where closed time-like curves exist, paths through spacetime that loop back on themselves, potentially allowing travel to the past. But these solutions require exotic conditions, rotating universes, infinitely long spinning cylinders, wormholes threaded with matter that has negative energy. Whether any of this can exist in reality, whether backward time travel is possible even in principle, remains hotly debated. And what about the future of time itself? Will the universe last forever, or will time eventually come to an end? The answer depends on the fate of the cosmos, and here too uncertainty reigns. If dark energy continues to accelerate the expansion of the universe, then galaxies will recede from each other faster and faster until they disappear beyond the horizon of observation. Stars will exhaust their fuel and die. Even black holes will eventually evaporate. The universe will become cold, dark, and empty, approaching what is sometimes called heat death, a state of maximum entropy where nothing interesting can happen anymore because no energy gradients remain. But maybe that is not the end. Maybe the universe will collapse back in on itself in a big crunch, reversing the expansion and ending in a singularity that mirrors the Big Bang. Maybe the universe cycles, expanding and contracting eternally, each cycle wiping away the previous one and starting fresh. Maybe dark energy will change in some unexpected way, leading to a big rip that tears apart galaxies, stars, planets, atoms, even the fabric of spacetime itself. Or maybe we are completely wrong about everything and the universe has surprises in store that we cannot begin to anticipate. The distant future is as mysterious as the distant past, the large-scale structure as puzzling as the subatomic realm. Everywhere we look, mysteries abound. And that is just considering the universe as it is. What about the universes that might be, the realities that could exist but do not? Mathematics is filled with structures and objects that seem to have a life of their own, existing independently of the physical world. Numbers, for example. The number 3 existed before humans did, before Earth formed, before the universe began. 3 is 3 whether anyone is around to count or not. The Pythagorean theorem was true long before Pythagoras discovered it. Mathematical truths seem eternal, necessary, existing outside space and time. But what does it mean for a mathematical object to exist? Is there a Platonic realm of perfect forms where all possible mathematical structures reside? And if so, is the physical universe just one of these structures somehow made real, selected from the vast space of mathematical possibilities? Some physicists, most notably Max Tegmark, have proposed that the universe is a mathematical structure, that physical existence and mathematical existence are the same thing. Every mathematically consistent universe exists in some sense, and we happen to find ourselves in one that permits observers like us. This is the mathematical universe hypothesis, and it is as bold and bizarre as any idea in all of science. If true, it means there are infinitely many other universes, corresponding to every possible mathematical structure. Some would be similar to ours, governed by slightly different laws or constants. Others would be radically different, unrecognizably alien, perhaps not even containing space or time as we understand them. All of them would be equally real, equally existent, differing only in their mathematical properties. Can this possibly be true? Is reality really this extravagant, this profligate with existence? Or is there something special about our universe, some reason why this particular mathematical structure is instantiated while others remain mere abstractions? We do not know. We may never know. But the question itself reveals how far we are from a complete understanding of existence. And then there are the mysteries we cannot even properly formulate yet, the unknown unknowns that might be the most significant discoveries of all. History teaches us that the biggest breakthroughs often come from unexpected directions, from observations that do not fit the prevailing theories, from questions we did not know to ask. Who, before the 20th century, would have imagined that space and time are not absolute? Who would have predicted quantum entanglement or the expansion of the universe or the wave-particle duality of matter? These discoveries came as complete surprises, overturning centuries of established understanding. What surprises await us? What observations will future telescopes make that will shatter our current worldview? What experiments will future particle accelerators perform that will reveal new layers of reality? What mathematical structures will future theorists discover that will unify physics in ways we cannot currently conceive? We cannot predict the next revolution in understanding, almost by definition. If we could, we would already have had it. But we can point to places where our current theories seem incomplete or unsatisfying, where cracks in the edifice suggest something deeper lurking beneath. The cosmological constant problem, for instance. Why is dark energy so weak? Theory predicts it should be vastly stronger, so strong that the universe would fly apart almost instantly. The measured value is smaller than theoretical expectations by a factor of something like 10 to the power of 120. This is not a small discrepancy. It is the worst prediction in the history of physics, suggesting that something fundamental is wrong with our understanding. Or consider the hierarchy problem. Why is gravity so much weaker than the other fundamental forces? The electromagnetic force, for example, is about a billion times stronger than gravity. This enormous gap seems unnatural, suggesting that either we are missing something or that we live in a very special, finely tuned universe. Various theories, supersymmetry, extra dimensions, technicolor, have been proposed to explain this hierarchy, but none have been confirmed. And what about the arrow of time problem we touched on earlier? Why does the universe have a direction to its evolution? Why do we remember the past but not the future? Why does cause precede effect? Our fundamental theories do not distinguish between past and future, and yet experience clearly does. Something is missing from our description. These anomalies, these puzzles, these places where theory and observation or intuition clash, these are the promising hunting grounds for future discoveries. They point toward gaps in our knowledge, holes that need to be filled. And filling those holes might require radical new ideas, concepts we have not yet imagined, mathematics we have not yet invented. There is also the very real possibility that we will develop entirely new ways of observing the universe, methods that reveal phenomena we currently cannot detect. Gravitational wave astronomy is a recent example. For most of history, we could only study the cosmos through light, visible light, then radio waves, X-rays, gamma rays, the entire electromagnetic spectrum. But gravitational waves are something different, ripples in spacetime itself produced by violent cosmic events. The first direct detection came only in 2015, opening a completely new window on the universe. Now we can hear black holes colliding, neutron stars merging, perhaps even echoes from the Big Bang itself. What else might we discover with this new sense? And gravitational waves are just one example. What if we could detect neutrinos more efficiently? These nearly massless particles flood through the universe, passing through matter almost unimpeded. They carry information from the cores of stars, from supernovae, from the Big Bang. Better neutrino detectors could reveal secrets hidden from light-based astronomy. What if we could detect dark matter directly, capturing those elusive particles in sophisticated detectors deep underground? What would they tell us about the invisible scaffolding that shapes the cosmos? What if we could probe the quantum vacuum itself, measuring the tiny fluctuations in empty space that quantum mechanics predicts? What if we could create and study exotic states of matter that do not exist anywhere naturally, pushing the boundaries of what is possible? What if we could build quantum computers powerful enough to simulate complex systems, biological molecules, chemical reactions, even small pieces of the universe itself, allowing us to explore reality through computation rather than just observation? Each new tool, each new technique, each new way of gathering information has the potential to reveal something unexpected. And in science, the unexpected is where the real breakthroughs happen. Consider also the possibility of phenomena that do not fit into our current taxonomies at all. We categorize the universe into matter and energy, particles and forces, space and time. But what if there are aspects of reality that do not fit these categories? What if there are entities or processes that are neither matter nor energy in the usual sense? What if the universe contains structures or properties that our current conceptual framework simply cannot accommodate? This might sound like vague speculation, but history shows it is not so far-fetched. Before discovering the quantum realm, physicists had no category for wave-particle duality. Before relativity, nobody conceived that space and time could merge into spacetime. Before dark energy, the notion of a cosmological constant that caused repulsion rather than attraction was considered a mistake Einstein made and later retracted. New discoveries often require new concepts, new categories, new ways of carving up reality. And we must not forget the possibility of engineering marvels that could transform not just what we know but what we can do. Could we harness dark energy for propulsion, using the expansion of space itself to travel vast distances? Could we manipulate spacetime, creating wormholes for faster-than-light travel or time machines for visiting the past? Could we tap into the quantum vacuum, extracting energy from fluctuations in empty space? Could we create artificial black holes or mini Big Bangs in laboratories, studying conditions of extreme physics directly rather than just observing them from afar? Some of these ideas sound like pure fantasy, violations of everything we think we know. And perhaps they are. Perhaps many of the things we might imagine doing are impossible, forbidden by deep principles we have yet to understand. But perhaps not. Perhaps the universe is more malleable than we realize, more subject to manipulation by sufficiently advanced intelligence. We will not know until we try, until we push the boundaries of what is possible and see where they bend or break. There is also the question of whether life and intelligence themselves might be more widespread or varied than we suppose. We search for life as we know it, carbon-based, requiring liquid water, metabolizing chemical energy. But could life arise in radically different forms? Could there be silicon-based life, or life in liquid methane, or life that exists in the plasma of a star's corona, or even life based on patterns of magnetic fields in space? Could consciousness emerge in substrates other than biological neurons, in networks of quantum particles, or clouds of interstellar dust, or the fabric of spacetime itself? These questions push us to examine our assumptions about what life is, what intelligence requires, what consciousness entails. If we define these concepts too narrowly, based only on the single example we know, we might miss entirely different forms of organization and awareness that exist but do not resemble us. Expanding our definitions might reveal that the universe is far more alive, far more conscious, far more populated than we ever imagined. And what of the ultimate questions, the ones that have haunted philosophy for millennia? Why does the universe exist at all? Why is there something rather than nothing? This might seem like a question beyond the reach of science, but physics has begun to grapple with it. Some theories suggest that the universe could arise spontaneously from quantum fluctuations, that nothing is inherently unstable and must give birth to something. Others propose that the universe is eternal, with no beginning and therefore no need for creation. Still others suggest that the question itself is misguided, that asking why about the totality of existence is like asking what is north of the North Pole, a category error that arises from trying to apply concepts like causation outside their domain of validity. And what about meaning and purpose? Science describes how the universe works, but does it work for any reason? Is there a point to it all, or is existence just a brute fact, meaningless and purposeless? Here we truly reach the boundary between science and philosophy, between what we can observe and measure and what we can only wonder about. But even here, new discoveries might constrain or inform our thinking. If we found that consciousness or life or intelligence were built into the structure of the universe, encoded in its laws or constants, that might suggest purpose. If we found that our universe was designed or created by some prior intelligence, advanced aliens or beings from a parent universe, that would push the question back but not eliminate it. If we found that meaning is something observers create rather than discover, that might shape how we think about purpose and value. The point is that even the deepest metaphysical questions might not be forever beyond the reach of inquiry. As our knowledge grows, as our understanding deepens, we may find that questions we thought were purely philosophical turn out to have empirical components, aspects that can be investigated and tested and resolved. So where does this leave us? What can we conclude about whether there is anything left to discover? The answer, overwhelming and undeniable, is yes. Emphatically yes. The universe is not running out of mysteries. We are not approaching the end of discovery. If anything, we are in the early stages of understanding, having barely scratched the surface of what can be known. Every answer reveals new questions. Every solution exposes new problems. The more we learn, the more we realize how much we do not know. And this is not a failure or a flaw, it is the glory and the wonder of the scientific enterprise. We live in an age of unprecedented discovery. Our telescopes are more powerful than ever, peering deeper into space and further back in time. Our particle accelerators probe smaller scales and higher energies. Our computers simulate ever more complex systems. Our understanding of biology, of neuroscience, of materials, of climate, of everything, continues to grow at an accelerating pace. We are making progress on problems that seemed intractable just decades ago. We are asking questions that previous generations could not even formulate. And yet the horizon keeps receding. For every question answered, two more arise. The tree of knowledge keeps branching, each branch splitting into more branches, the structure growing ever more intricate and interconnected. Dark matter and dark energy remind us that the cosmos is mostly mysterious. Quantum mechanics reminds us that reality is stranger than intuition suggests. Consciousness reminds us that the universe contains not just objects and forces but awareness and experience. The origin of life reminds us that existence itself is a puzzle. The possibility of extraterrestrial intelligence reminds us that we might not be alone. The prospect of advanced AI reminds us that intelligence could transcend biology. The nature of time reminds us that even our most basic experiences are deeply mysterious. What will we discover next? What breakthrough lurks just around the corner, waiting for the right observation or the right insight? What revolution in understanding will transform how we see ourselves and our place in the cosmos? We cannot know. We cannot predict. But we can be certain that surprises await, that mysteries remain, that the universe has not finished revealing its secrets. Perhaps dark matter will turn out to be something completely unexpected, not new particles but a modification of gravity itself at large scales, requiring a revision of general relativity. Perhaps dark energy will vary in time or space, leading to a future very different from the one we predict. Perhaps we will discover additional dimensions of space, or find that spacetime is discrete rather than continuous, or learn that the universe is a hologram or a simulation. Perhaps we will detect gravitational waves from the Big Bang itself, revealing what happened in the very first moments of cosmic history. Perhaps we will find life on Mars or Europa or in the clouds of Venus, or detect a signal from an alien civilization among the stars. Perhaps we will unlock the secrets of the quantum realm, learning how to manipulate matter and energy at will, building materials and machines with properties that seem magical today. Perhaps we will solve the mystery of consciousness, understanding how matter becomes aware and what awareness truly is. Perhaps we will merge with our machines, transcending biological limitations and expanding our minds in ways we cannot currently imagine. Perhaps we will develop new forms of mathematics, new ways of thinking, that allow us to grasp truths currently beyond our comprehension. Or perhaps the discoveries will come from directions we have not even considered, from questions we do not yet know to ask. Perhaps the universe will surprise us in ways we cannot anticipate, revealing wonders and horrors and beauties we cannot imagine. Perhaps the most profound mystery is one we have not yet encountered, hidden not in the depths of space or the quantum foam but somewhere we have not thought to look. This is the human condition, to be small and temporary in a vast and ancient universe, and yet to possess minds capable of contemplating infinity and eternity. We are made of star stuff, atoms forged in the cores of long-dead suns, organized by evolution into structures capable of awareness, able to look back at the cosmos and recognize our origins. We are the universe become conscious of itself, matter pondering matter, existence contemplating existence. And we are driven to understand. Not because understanding will make us happy or safe or immortal, though it might help with all of these, but because understanding is what we do. It is what makes us human. We are the species that asks why, that seeks patterns, that craves explanation. We cannot help ourselves. Give us a mystery and we must solve it. Give us a question and we must answer it. Show us the universe and we must comprehend it. So we build telescopes and accelerators, we develop theories and conduct experiments, we observe and measure and calculate and dream. We push back against the darkness of ignorance, one small light at a time, illuminating corners of reality that were previously hidden. The work is difficult, often frustrating, sometimes dangerous. Progress is slow and hard-won. Dead ends are common. Mistakes are made. But we persist because we must, because the alternative, to accept ignorance, to stop questioning, to cease wondering, is unthinkable. And here is the beautiful paradox: the more we learn, the more wonder we feel. Knowledge does not diminish mystery, it deepens it. Understanding does not make the universe less amazing, it makes it more so. Every discovery reveals greater depths, wider vistas, stranger truths than we imagined. The cosmos keeps unfolding, keep revealing itself to be richer and more intricate than any story we could have invented. Think about what we have learned in just the last century. That the universe had a beginning. That space can expand. That time can slow down. That matter and energy are interchangeable. That particles can be waves and waves can be particles. That nothingness seethes with activity. That the observer affects the observed. That most of the universe is invisible. That reality is probabilistic at its core. Any one of these insights would be revolutionary. Together, they constitute a transformation in understanding so profound that it is difficult to overstate. And we are not finished. We will never be finished. There will always be more to discover, more to learn, more to understand. The universe is apparently infinite in extent, eternal in duration, and boundlessly complex in its structure. Even if we had infinite time and infinite resources, we might never exhaust its mysteries. And that is exactly as it should be. A universe fully explained, with no mysteries remaining, would be a dead universe, a completed puzzle no longer interesting to contemplate. We are blessed, or perhaps cursed, to live in a cosmos that exceeds our grasp, that challenges us, that demands our attention and our intelligence and our creativity. We are fortunate to inhabit a reality so strange and wonderful that even our best theories sound like fever dreams, where darkness outweighs light and energy pushes space apart, where cats can be alive and dead simultaneously and particles connected across the universe influence each other instantly, where time may be an illusion and consciousness an emergence and life a cosmic accident that need not have happened but did. Is there anything else to discover in the universe? The question almost answers itself. Of course there is. How could there not be? We have barely begun. We are children playing at the edge of an infinite ocean, having collected a few pretty shells while the vast deep remains unexplored. We are mapmakers who have charted a few islands while continents await discovery. We are readers who have turned only the first pages of an endless book. The discoveries of the future will likely dwarf those of the past. The mysteries we uncover will make current puzzles seem trivial. The understanding we achieve will reveal how little we truly comprehended even our most confident theories. And through it all, the universe will keep surprising us, keep challenging us, keep inviting us deeper into its secrets. So yes, there is more to discover. More than we can imagine. More than we can explore in 1,000 lifetimes or 10,000. The universe is not stingy with its mysteries. It is generous beyond measure, offering puzzle after puzzle, wonder after wonder, truth after astonishing truth. Our task is simply to keep looking, keep questioning, keep seeking. To never lose the sense of wonder that draws us forward. To never stop asking why and how and what if. Because in the end, the greatest discovery may not be any particular fact or theory or insight, but rather the realization that discovery itself is endless, that the quest for understanding is a journey without destination, a path that winds ever onward through landscapes of increasing beauty and strangeness. We are explorers in a universe that rewards exploration, seekers in a cosmos that responds to seeking, questioners of a reality that seems almost designed to provoke questions. And perhaps that is the deepest truth of all, that we are meant to wonder, meant to question, meant to seek. Not because we will ever arrive at final answers or complete understanding, but because the seeking itself is the point, the journey is the destination, the questions are more important than the answers. We discover not to finish but to continue, not to close the book but to turn the page, not to end the mystery but to deepen it. So look up at the night sky and ask what lies beyond those stars. Look down at your hand and ask how consciousness arises from matter. Look around at the world and ask why it exists at all. The universe is waiting to answer, waiting to reveal, waiting to astonish you. And the most incredible discoveries, the most profound insights, the most transformative breakthroughs, still lie ahead, waiting in the darkness, ready to illuminate our understanding in ways we cannot yet imagine but soon will experience. The cosmos beckons. The mysteries call. The adventure continues. And there is so much more to discover than we have yet dared to dream. Beyond these cosmic riddles lies an entire menagerie of bizarre objects that challenge our understanding of matter itself. Consider neutron stars, collapsed stellar cores so dense that a teaspoonful would weigh as much as Mount Everest. Here, in objects barely 20 kilometers across, matter is compressed to densities that simply do not exist anywhere else in the universe except perhaps in the cores of colliding neutron stars or inside black holes themselves. The atoms are crushed out of existence. Electrons are forced into protons, creating an object made almost entirely of neutrons packed so tightly that the entire star becomes, in effect, a single atomic nucleus the size of a city. What happens to the laws of physics under such extreme conditions? We think we know, but we are extrapolating far beyond anything we can test in laboratories. The pressures inside neutron stars exceed anything we can recreate. The magnetic fields of certain neutron stars called magnetars are so intense they would tear apart atoms from thousands of kilometers away, and if you got too close, they would literally rearrange the molecular bonds in your body, transforming your chemistry into something unrecognizable. These fields are a quadrillion times stronger than Earth's magnetic field, strong enough to warp the quantum vacuum itself. Magnetars occasionally undergo starquakes, their solid crusts crack and shift like tectonic plates but with energies that would dwarf anything geological. When this happens, they release bursts of gamma rays and X-rays so powerful that they can be detected across the galaxy. One such burst in 2004 briefly outshone the full moon despite coming from a star 50,000 light-years away. The radiation pulse ionized Earth's upper atmosphere, affecting radio communications. This was not a supernova, not a black hole collision, just a crack in the crust of a dead star. The sheer violence of the cosmos sometimes defies comprehension. And then there are pulsars, neutron stars that spin hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses. When they were first discovered, their signals were so regular, so precise, that astronomers briefly wondered if they might be artificial, beacons from alien civilizations. Nature, it turned out, could create clocks far more accurate than anything we had built. The timing of pulsar signals is so stable that we use them to test relativity, to search for gravitational waves, even to navigate spacecraft. These dead stars have become tools, instruments in our exploration of fundamental physics. But what lies at the center of a neutron star? Is there a core of even denser matter, quarks freed from their usual confinement inside protons and neutrons, forming what physicists call strange quark matter? Could this exotic substance be stable? Could it, if it exists, convert ordinary matter into more strange matter through a kind of chain reaction? There are theories suggesting that strange quark matter might be the true ground state of nuclear material, that all atomic matter is actually metastable, waiting for the right trigger to transform into something denser and more fundamental. If true, a single strange quark nugget could theoretically convert an entire planet. This scenario, while speculative and considered unlikely, remains an unsettling possibility lurking in the equations. Travel further back in cosmic time and you encounter quasars, the brilliant hearts of young galaxies powered by supermassive black holes consuming matter at prodigious rates. These objects are so luminous that a single quasar can outshine an entire galaxy containing hundreds of billions of stars. They existed when the universe was young, less than 1 billion years old, and their very existence poses a problem. How did black holes millions or billions of times more massive than the Sun form so quickly? Standard theories of stellar collapse and black hole growth struggle to explain their early appearance. Either black holes can grow faster than we thought, or they started bigger than we imagined, or something about the early universe was fundamentally different from what our models predict. Observing quasars is like looking through a time machine. The light we see left them billions of years ago, showing us the universe in its adolescence. Between then and now, that light has traveled across expanding space, passing through clouds of gas, skimming past galaxies, occasionally being bent and distorted by gravitational lensing. By the time it reaches our telescopes, it carries information not just about the quasar itself but about everything it encountered along the way. Quasars are probes, natural experiments that test our understanding across cosmic scales. Yet for all our observations of these distant beacons, we still grapple with basic questions about cosmic structure. Why does the universe look the way it does on the largest scales? Why do galaxies cluster into filaments and walls surrounding vast voids, creating a cosmic web that resembles neurons in a brain or the cellular structure of bone? These patterns emerged from tiny quantum fluctuations in the earliest moments after the Big Bang, amplified by gravity over billions of years. But the details remain murky. Computer simulations can reproduce the observed structure, but only by invoking dark matter and dark energy. Without these invisible components, the predictions fail completely. And speaking of invisible components, what about cosmic strings? These are hypothetical defects in spacetime, incredibly thin but potentially stretching across the cosmos, left over from phase transitions in the early universe, like cracks in ice forming as water freezes. If they exist, cosmic strings would have extraordinary properties: immense tension, the ability to warp spacetime dramatically, perhaps even the potential to create closed time-like curves that could allow time travel. Detecting them would require observing their gravitational effects, perhaps through the distinctive way they would lens light or generate gravitational waves. So far, we have found nothing, but the search continues. Then there is the mystery of antimatter, that mirror image of ordinary matter where every particle has an opposite twin with reverse charge. When matter meets antimatter, they annihilate in a flash of pure energy. This should have happened to the entire universe shortly after the Big Bang. The initial conditions should have produced equal amounts of matter and antimatter, which should have destroyed each other completely, leaving nothing but radiation. And yet here we are, made of matter, surrounded by matter, living in a universe apparently devoid of antimatter. Something broke the symmetry. Some process favored matter over antimatter by the tiniest margin, perhaps 1 part in a billion, but that was enough. That slight asymmetry is the reason anything exists at all. What caused this imbalance? We have hints. The standard model of particle physics allows for processes that violate certain symmetries, creating conditions where matter could be favored. But the effects predicted are too small. They cannot account for the observed asymmetry. Something else must have happened, some additional mechanism operating in the early universe that we have not yet identified. Finding it would explain why we exist, why there is a universe full of stars and planets and life instead of nothing but light echoing through empty space. This brings us to one of the deepest puzzles in all of physics: why is the vacuum energy not catastrophically large? According to quantum field theory, empty space should be seething with virtual particles that constantly pop into and out of existence, and these fluctuations should contribute to the energy of the vacuum. When you calculate how much energy this should produce, you get a number that is absurdly, incomprehensibly large, so large that space itself should be expanding at a rate that would tear apart atoms, prevent any structures from forming, make the universe uninhabitable. This is the vacuum catastrophe, or the cosmological constant problem, and it represents the worst mismatch between theory and observation in the history of science. The measured vacuum energy, what we call dark energy, is tiny compared to theoretical predictions. It is not zero, which would be one way to solve the problem, but it is small enough to allow for galaxies and stars and life. Why? Nobody knows. Perhaps there is some mechanism that cancels out the quantum contributions, reducing them to nearly nothing but not quite. Perhaps our calculations are fundamentally wrong, missing some crucial ingredient. Perhaps the answer lies in quantum gravity, in the way spacetime itself behaves at the smallest scales. This mystery sits at the intersection of quantum mechanics, general relativity, and cosmology, demanding insights from all three for its resolution. Descending to even tinier scales, we approach the Planck length, roughly 10 to the power of -35 meters, the smallest distance that has meaning in our current theories. At this scale, quantum fluctuations of spacetime itself become important. Space becomes foamy, uncertain, discontinuous. Our familiar notions of smooth geometry break down. Some theories suggest that spacetime is not fundamental but emergent, built from something more basic, perhaps qubits of information, perhaps networks of quantum entanglement, perhaps mathematical structures we have not yet discovered. If this is true, then space and time are like temperature or pressure, properties that emerge from underlying microscopic dynamics rather than being fundamental themselves. This leads to fascinating speculation about emergent gravity, the idea that gravitational attraction is not a fundamental force but arises from thermodynamic principles or information theory. Just as pressure emerges from countless molecular collisions without being fundamental, perhaps gravity emerges from something deeper. Some physicists, most notably Eric Verland, have proposed that gravity is an entropic force, a consequence of the statistical behavior of information on holographic screens. While controversial and not yet accepted, such ideas point toward radical reconceptions of spacetime and gravity that might ultimately lead to the quantum theory we seek. Information itself becomes a central player in these discussions. What is information? Is it physical? Does it have mass or energy? Can it be destroyed? The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary, like a hologram where a three-dimensional image is stored on a two-dimensional surface. This hints that our three-dimensional reality might be a projection, that the fundamental description of the universe might be written in a language we have not yet learned to speak, on a surface we cannot see. But while physicists wrestle with the nature of spacetime and information, biologists face mysteries closer to home yet equally profound. The genetic code, the mapping between DNA sequences and amino acids that builds proteins, appears nearly optimal. Of all the possible ways to assign 64 codons to 20 amino acids, the actual code minimizes errors, protects against mutations, and clusters similar amino acids together. This suggests optimization, but optimization by what process? Did evolution explore many possible genetic codes before settling on this one? Did life start multiple times with different codes, with only the best version surviving? Or is there something about chemistry and physics that makes this particular code inevitable? And why does all life on Earth use the same code? The universality of the genetic code across bacteria, plants, animals, fungi, everything, suggests a single origin. We all descend from one common ancestor, some primordial cell that lived billions of years ago and whose descendants eventually diversified into every species that has ever existed. But was this ancestor itself the first life, or merely the survivor of earlier, simpler forms that left no descendants? Did life arise multiple times on Earth, with most lineages going extinct and only one persisting? The question remains open. Could life have originated elsewhere and been transported to Earth? Panspermia, the idea that life spreads between worlds on meteorites or comets, remains possible. We know that rocks are occasionally blasted off Mars by asteroid impacts and eventually land on Earth. We know that some bacteria can survive in space for extended periods. We know that organic molecules exist in comets and asteroids. The pieces are there for interplanetary contamination. Perhaps life began on Mars when it was warmer and wetter, then seeded Earth after the Martian environment became hostile. Perhaps life is cosmic, spreading throughout the galaxy wherever conditions permit, carried on currents of dust and debris between the stars. But this merely displaces the question. Even if life came from elsewhere, it still had to start somewhere. And wherever it started, however it started, it demonstrated that non-living chemistry can become living biology. This transition remains one of the great unknowns. We can imagine scenarios, construct plausible pathways, demonstrate pieces of the puzzle in laboratories. But we cannot yet take a sterile flask of chemicals and coax genuine life into existence. We cannot bridge that final gap between complex chemistry and simple biology. Meanwhile, life as we know it keeps surprising us with its tenacity and diversity. Extremophiles, organisms that thrive in conditions we would consider lethal, have rewritten our understanding of life's possibilities. Bacteria living in boiling water. Microbes thriving in acid strong enough to dissolve metal. Organisms surviving radiation doses that would instantly kill humans. Microbes extracted from rocks kilometers underground, living without sunlight, metabolizing minerals and hydrogen gas, possibly isolated from the surface world for millions of years. Tardigrades, those microscopic water bears, surviving the vacuum of space, extreme cold, extreme heat, pressures 6 times deeper than the deepest ocean trench. Each discovery of life in impossible places expands the habitable zone, increases the range of environments we must consider when searching for extraterrestrial biology. If life can exist in Earth's harshest environments, why not in the acidic clouds of Venus, or the subsurface oceans of Europa, or the hydrocarbon lakes of Titan, or the salt deposits of Mars, or anywhere chemistry becomes sufficiently complex and energy sufficiently available? But why stop at natural life? We are developing the ability to create artificial life, to design organisms from scratch or modify existing ones beyond recognition. Synthetic biology is moving from theory to practice. Constructing genetic circuits, engineering metabolic pathways, building biological computers. We have already created bacteria with expanded genetic codes, incorporating unnatural amino acids into proteins, producing molecules that never existed in nature. We have synthesized entire genomes and transplanted them into cells, creating organisms whose hereditary information was written by human minds rather than shaped by evolution. Where does this capability lead? Could we design organisms to survive on other worlds, creating life adapted to Martian conditions or the atmosphere of Venus? Could we engineer microbes to produce medicines, clean up pollution, manufacture materials, compute answers to problems too difficult for electronic computers? Could we create entirely new forms of life, not descended from any natural organism, with different chemistry, different information storage, different reproduction methods? The line between biology and technology blurs. Life becomes designable, programmable, controllable in ways evolution never permitted. And if we can engineer biology, might we engineer ourselves? The prospect of human enhancement, genetic, pharmaceutical, mechanical, digital, looms larger every year. We already augment ourselves with technology, glasses to correct vision, pacemakers to regulate hearts, cochlear implants to restore hearing, pharmaceutical aids to sharpen attention or regulate mood. These modifications are accepted, unremarkable. But what about enhancements that go beyond repair to augmentation? What about genetic editing to eliminate disease or enhance intelligence? What about neural interfaces that connect brains directly to computers? What about radical life extension, treating aging itself as a disease to be cured rather than an inevitability to be accepted? The biology of aging presents its own mysteries. Why do we age? Why does the body wear out, accumulating damage faster than it can be repaired? Evolution has no incentive to keep us alive past reproductive age, but that hardly explains the mechanisms. Telomeres shorten with each cell division. DNA accumulates mutations. Proteins misfold and aggregate. Mitochondria become less efficient. Stem cells become exhausted. Senescent cells accumulate, secreting inflammatory signals. These processes are known, but are they causes or symptoms? Can they be reversed? Several research programs aim to find out, treating aging not as inevitable but as a medical problem with potentially medical solutions. Imagine humans living hundreds of years, their bodies perpetually maintained in youth. How would this change society, culture, our sense of meaning and urgency? Would extended lifespans lead to stagnation, with old ideas and old leaders never making way for new ones? Or would it usher in a golden age, with experienced minds accumulating centuries of knowledge and wisdom? These questions move from biology toward philosophy, from what we can do toward what we should do. The brain itself remains deeply mysterious despite decades of neuroscience research. We know which regions are involved in language, in vision, in motor control, in emotion. We can watch neurons fire and see how patterns of activity correlate with thoughts and sensations. But we still do not understand memory at a fundamental level. How are experiences encoded? Where are memories stored? Why do we forget? How does the brain compress and index vast amounts of information so that we can recall details decades later? These are not trivial questions. Memory makes us who we are, provides continuity to our identities, connects our past and present and anticipated future into a coherent narrative. And then there is language, that uniquely human capacity that sets us apart from every other species. How did it arise? When did our ancestors start speaking? What changes in the brain or vocal tract enabled complex syntax and abstract thought? Other animals communicate, bees dance, birds sing, whales produce complex vocalizations, but none approach the flexibility and generativity of human language. We can produce and understand sentences we have never heard before, combine words in novel ways, express ideas about things that do not exist. Talk about the past and future and hypothetical alternatives to reality. This capacity seems qualitatively different from animal communication, suggesting something fundamental changed in our cognitive architecture. Some researchers believe language and thought are deeply intertwined, that our ability to think abstractly depends on linguistic structures. Others argue that thought precedes language, that concepts exist independent of words. Does the language you speak shape how you think? Do speakers of different languages perceive reality differently? These questions touch on the relationship between mind and culture, between biology and society, between individual cognition and collective understanding. Culture itself evolves, not through genes but through ideas. Memes, units of cultural information, spread and mutate and compete for attention much like genes compete for reproductive success. Technologies build on earlier technologies. Scientific theories replace previous theories. Art movements respond to preceding movements. This cultural evolution operates on timescales far faster than biological evolution, centuries or decades rather than millennia, and has transformed human life more radically than any change in our DNA. We are approaching what some call the technological singularity, a hypothetical point where artificial intelligence surpasses human intelligence and begins improving itself, leading to explosive growth in capabilities that we cannot predict or control. Whether this will happen, when it might happen, and what it would mean remain hotly debated. Pessimists worry about existential risks, machines with goals misaligned with human welfare, superintelligences that could dominate or destroy us. Optimists envision partnerships between human and artificial minds, combining our strengths to solve problems neither could tackle alone. The truth likely lies somewhere between nightmare and utopia, complicated and contingent on choices we have not yet made. But setting aside speculation about future AI, consider what such intelligences could discover if they surpass us. If human minds cannot fully grasp certain aspects of reality due to cognitive limitations, then post-human or artificial minds unbound by those limitations might perceive truths currently hidden from us. They might solve the mystery of quantum gravity, understand consciousness, determine the fate of the universe, answer questions we cannot even formulate. In a sense, the future of discovery might not belong to humanity alone but to whatever forms of intelligence we create or become. And what of alien intelligence? If it exists, if civilizations arise elsewhere and develop technology, what traces would they leave? We have searched for radio signals, but perhaps advanced civilizations use communication methods we have not imagined. We look for light from cities, heat signatures from power generation, industrial chemicals in planetary atmospheres. These are techno-signatures, evidence of technology rather than biology. But maybe truly advanced civilizations build structures on scales we have not considered. Dyson spheres enclosing entire stars to harvest their energy. Ring worlds or shell worlds providing enormous living space. Stellar engines capable of moving stars themselves. Computronium, matter reorganized into optimal substrates for computation. Such megastructures would be visible across interstellar distances, beacons of intelligence written across the sky. Why have we not seen them? This is another form of the Fermi paradox. If intelligence commonly builds such structures, the galaxy should be full of them. Our telescopes should see their signatures everywhere. The silence suggests either that intelligence is rare, or that it does not build such structures, or that something prevents civilizations from reaching that level of development. This something is sometimes called the Great Filter, an obstacle so difficult that most life or intelligence fails to pass it. The terrifying question is whether the filter lies behind us or ahead. If behind us, if the hard step was the origin of life, or the evolution of complex cells, or the emergence of intelligence, then we are lucky survivors and the galaxy is ours to explore. If ahead of us, if something typically destroys civilizations before they spread among the stars, then we are walking toward an unseen cliff. Perhaps the filter is self-destruction through war, pollution, climate change, engineered pandemics, or runaway AI. Perhaps it is physical, interstellar travel is simply too hard, too slow, too expensive for any civilization to manage. Perhaps it is sociological, advanced societies turn inward, focused on virtual realities or digital paradises, losing interest in physical expansion. Perhaps it is cosmic, some natural phenomenon we have not identified regularly sterilizes planets or destroys civilizations. We do not know. We are working with a sample size of one, ourselves, and extrapolating wildly. If we survive, if we spread beyond Earth, what would that expansion look like? Chemical rockets can barely escape our own gravity well. Reaching even the nearest star with current technology would take thousands of years. We need breakthroughs, fusion propulsion, antimatter drives, solar sails pushed by lasers, perhaps even the manipulation of spacetime itself. The Alcubierre drive, a theoretical warp engine that contracts space ahead of a spacecraft and expands it behind, remains a tantalizing possibility, though it requires exotic matter with negative energy density, the same stuff that might hold wormholes open, and we have no idea if such matter can exist or be produced. Alternatively, we might send not humans but seeds of humanity, frozen embryos, digital minds, self-replicating robots that build colonies on arrival. Such von Neumann probes could spread through the galaxy exponentially, each new outpost sending probes to further stars. Given millions of years, the entire galaxy could be explored and settled. This makes the Fermi paradox even stranger. If colonization is possible through self-replicating probes, why has no alien civilization done it? Where are the waves of probes that should have reached Earth long ago? The silence deepens. Perhaps we are simply early. Perhaps intelligence is rare and slow to emerge, and we happen to be among the first. Perhaps in 1 billion years the galaxy will be full of civilizations, but right now, in this cosmic moment, we are pioneers. This would explain the apparent emptiness without requiring any great filter. We are not uniquely special, just uniquely early, looking out at a universe not yet awakened to itself. Or perhaps the galaxy is full but using technologies or occupying spaces we have not imagined. Perhaps civilizations upload themselves into computers, existing as digital patterns, invisible to our searches. Perhaps they migrate into black holes or use dark matter for construction. Perhaps they exist in higher dimensions or parallel quantum branches. Perhaps they are here, observing us, choosing not to make contact for reasons we cannot understand. These explanations verge on unfalsifiable, but they remind us that absence of evidence is not always evidence of absence, especially when we barely know what evidence to seek. Returning from speculation about aliens to firmer ground, consider the ultimate fate of everything. If dark energy continues driving acceleration, galaxies will recede beyond our cosmic horizon, disappearing from view. Future astronomers trillions of years hence will see only the local galaxy group, isolated in a vast darkness, with no evidence that other galaxies ever existed. The cosmic microwave background will redshift into invisibility. The expansion history of the universe will be unobservable. Future scientists might develop completely different cosmologies, having lost the evidence we currently use to understand cosmic history. This is sobering. It suggests that our moment in cosmic time is special, that we can observe things that will eventually become unobservable, and that timing matters for what can be discovered. Eventually, stars will exhaust their fuel. Galaxies will go dark. Protons themselves might decay, given enough time, dissolving the very atoms that make up matter. Black holes will evaporate through Hawking radiation, slowly, impossibly slowly, but eventually completely. The universe approaches heat death. A state of maximum entropy where no energy gradients remain, no work can be done, no structures can exist, no thoughts can be thought. This is the big freeze, or the heat death, or simply the end, cold, dark, empty, eternal. Unless something else happens. Unless physics has more surprises. Unless quantum fluctuations eventually produce random configurations of particles that resemble observers, Boltzmann brains that flicker into existence and experience a moment of consciousness before dissolving back into chaos. Unless the universe cycles, collapsing and reborn in endless iterations. Unless new universes bud off from black holes or quantum foam, creating eternal inflation where universes spawn more universes forever. Unless. We do not know how the story ends because we have not yet finished reading the current chapter. And perhaps that is the ultimate answer to whether anything remains to be discovered. We are characters in a story whose plot we are still uncovering, inhabitants of a universe whose rules we are still learning, explorers on a journey whose destination remains unknown. Every answer leads to new questions. Every solution reveals deeper mysteries. The horizon of knowledge perpetually recedes, always just beyond our reach, always inviting us forward. So yes, there is more to discover. Vastly more. Not just details filling gaps in existing knowledge, but revolutionary insights that overturn established understanding. Not just answering known questions, but finding entirely new questions we have not yet thought to ask. The universe is not running out of secrets. If anything, it seems designed to keep us curious, to reward investigation with revelation, to ensure that the quest for understanding never ends. And in this endless quest lies both our challenge and our glory, to be creatures who wonder, who question, who seek, forever reaching toward truths that shimmer just beyond our grasp, forever approaching understanding that forever remains incomplete, forever discovering that reality is richer, stranger, and more magnificent than we ever dared imagine. The sky rains particles we barely understand. Every second, cosmic rays, high-energy protons and atomic nuclei accelerated to near-light speeds, slam into Earth's atmosphere from deep space. Most are mundane, the remnants of supernova explosions or emissions from pulsars. But occasionally, very occasionally, something extraordinary arrives, particles with energies so high they should not exist, energies exceeding anything our most powerful accelerators can produce by factors of millions. These are the ultra-high-energy cosmic rays, and they are deeply puzzling. A particle traveling at such energies should interact with the cosmic microwave background, losing energy through particle production, limiting how far it can travel. This is the GZK cutoff, named after the physicists who predicted it. No cosmic ray above a certain energy should reach us from sources more than a few 100 million light-years away. And yet we detect them. Not many, perhaps 1 per square kilometer per century, but they arrive nonetheless, impossibly energetic, apparently violating theoretical limits. What could accelerate particles to such extremes? The most violent processes we know, supernova explosions, black hole accretion, gamma-ray bursts, fall short. Perhaps colliding galaxies generate these energies in magnetic shocks spanning millions of light-years. Perhaps exotic objects we have not identified serve as natural particle accelerators dwarfing anything we can build. Or perhaps these cosmic rays are not ordinary particles at all but something stranger, the decay products of supermassive dark matter particles, or topological defects in spacetime, or remnants from the Big Bang trapped in some unknown configuration until randomly released. We capture these particles in vast detector arrays spread across deserts and mountains, watching for the showers of secondary particles they create when striking the atmosphere. Each event is precious, a message from the high-energy universe written in a language we struggle to translate. The arrival directions show no obvious pattern. Pointing randomly across the sky rather than clustering near powerful cosmic engines. This makes the mystery deeper. If the sources were nearby active galaxies or young pulsars, we should see correlations. The random distribution suggests either that the sources are very distant, beyond the theoretical limit, or very numerous and individually weak, or that magnetic fields in intergalactic space scramble the trajectories so thoroughly that we cannot trace them back to their origins. Then there are neutrinos from even stranger sources. In 2013, detectors buried deep in Antarctic ice recorded neutrinos with energies far exceeding those produced by known astrophysical processes. These particles had traveled through the Earth. Neutrinos interact so weakly with matter that the entire planet is essentially transparent to them, arriving from directions that pointed toward no obvious sources. Follow-up observations with optical and radio telescopes found nothing unusual in those regions of sky. Whatever created these high-energy neutrinos remains invisible to normal light. Some events seem to correlate with flaring galaxies, their supermassive black holes temporarily brightening as they consume matter. Others point toward blank regions of space. Could these be signals from dark matter annihilation, from evaporating primordial black holes, from cosmic strings releasing energy as they oscillate, or from processes we have not yet theorized? The detection of high-energy neutrinos opened a new channel of cosmic communication, but the messages remain cryptic. Meanwhile, the Large Hadron Collider at CERN recreates conditions not seen since microseconds after the Big Bang, smashing protons together at energies approaching 7 trillion electron volts. When particles collide at such energies, they briefly produce temperatures and densities that melt protons and neutrons into their constituent quarks and gluons, creating a state of matter called quark-gluon plasma. This plasma existed throughout the universe during its first microseconds, before things cooled enough for quarks to bind together into protons and neutrons. Studying this primordial substance reveals surprising properties. It behaves not like a gas of independent particles but like a nearly perfect fluid with almost no viscosity, flowing with less resistance than any other known substance, including liquid helium. The quarks and gluons remain strongly coupled even when liberated from protons, suggesting that the transition from confined to deconfined matter is more subtle than simple pictures suggest. This has implications for neutron star physics. Perhaps the cores of the densest neutron stars contain quark matter, or perhaps the transition never fully occurs and nuclear matter remains bound even under extreme compression. The collider also searches for deviations from the Standard Model, that remarkably successful theory describing fundamental particles and forces. So far, the Standard Model has passed every test, predicting particle behaviors with astonishing precision. And yet it cannot be complete. It does not include gravity. It does not explain dark matter. It does not account for neutrino masses, which were discovered experimentally but not predicted by the theory. It leaves the Higgs mass unstable against quantum corrections, the hierarchy problem, requiring either fine-tuning or new physics to stabilize it. Physicists search for supersymmetry, a proposed symmetry that pairs every known particle with a heavier partner. Supersymmetric particles would solve several problems simultaneously, stabilizing the Higgs mass, providing dark matter candidates, unifying the fundamental forces at high energies. The theory is elegant, mathematically beautiful, and seemingly wrong. Experiments find no evidence for supersymmetric particles up to energies far higher than early predictions suggested. Either supersymmetry is broken at higher scales than expected, or nature chose a different solution. Perhaps extra dimensions exist but are compactified, curled up so small that we cannot detect them. String theory requires additional spatial dimensions, typically 6 or 7 beyond the familiar 3. Each twisted into complex geometric shapes called Calabi-Yau manifolds. The specific geometry determines what particles and forces exist in the observable three-dimensional universe, like how the shape of a musical instrument determines which notes it can play. Different geometries produce different physics. This leads to the landscape problem. String theory appears to allow an enormous number of possible vacuum states, perhaps 10 to the power of 500 or more, each corresponding to a different universe with different laws. Is our universe just one possibility among countless others? If so, what determines which possibility is realized? The anthropic principle suggests that we find ourselves in a universe compatible with our existence. We could not observe any other kind, but this explanation feels unsatisfying, more like giving up than understanding. It transforms physics from a search for unique necessary truths into a study of arbitrary historical accidents. Some physicists embrace this conclusion, arguing that the universe has no obligation to satisfy our preferences for elegant unique explanations. Others continue searching for principles that might select our universe uniquely from the landscape of possibilities. Consider the fundamental constants of nature, the speed of light, Planck's constant, the gravitational constant, the electron charge, the masses of particles. These numbers appear arbitrary, not derivable from any deeper principle we know. Why does the electron have the mass it has? Why is the fine structure constant approximately 1 over 137? We can measure these constants with exquisite precision, but we cannot explain them. They are input parameters, numbers we must plug into our equations rather than outputs predicted by theory. Some constants seem deeply related. The ratio between electromagnetic and gravitational forces, for instance, involves enormous numbers, roughly 10 to the power of 40. This appears in multiple contexts, the ratio between electric and gravitational forces between protons, the ratio between the size of the universe and atomic scales, the ratio between the age of the universe and atomic time scales. These large number coincidences puzzled physicists for decades. Are they meaningful? Do they hint at deeper connections we have not uncovered? Or are they merely accidents, consequences of when and where we happen to observe the universe? Dirac noticed these coincidences and proposed that they might vary with time, that the gravitational constant might weaken as the universe ages, preserving certain numerical relationships. Tests have found no evidence for such variation. The constants appear constant, at least within observational precision across billions of years. Yet the question persists, why these values? Could they be different? In other universes, assuming such exist, do constants take different values? And if so, how sensitive is the existence of complexity, stars, planets, chemistry, life, to these parameters? We know that small changes would be catastrophic. Strengthen gravity slightly and stars burn faster, exhausting their fuel before planetary systems stabilize or life evolves. Weaken it and stars might never ignite, leaving a dark cold universe of gas clouds. Adjust the strong nuclear force and nuclei become unstable, preventing complex atoms. Modify electromagnetic interactions and chemistry changes beyond recognition. The universe appears calibrated for complexity, poised in a narrow region of parameter space permitting interesting phenomena. This fine-tuning either requires explanation or demands acceptance. Theists see design, evidence of a creator selecting parameters purposefully. The multiverse offers naturalistic explanation. If all possible parameter combinations exist somewhere, we necessarily find ourselves where conditions permit observers. Critics note this explains nothing predictively, it accommodates any observation by invoking unobservable universes. The debate continues without resolution, touching physics, philosophy, and metaphysics simultaneously. Stepping away from cosmology toward complexity itself, we encounter mysteries in how order emerges from chaos. Simple rules produce intricate patterns. Cellular automata, grids where each cell follows deterministic rules based on neighbors, can generate endless complexity from trivial starting conditions. Conway's Game of Life, perhaps the most famous example, creates structures that move, reproduce, even compute, all from a handful of rules about birth and death of cells. This suggests that complexity might be inevitable, that simple underlying physics naturally produces rich emergent phenomena. Water molecules follow straightforward electromagnetic interactions, yet collectively they form snowflakes of infinite variety, each unique, each exhibiting six-fold symmetry reflecting molecular geometry. Sand grains obeying gravity and friction self-organize into piles with characteristic slopes, occasionally experiencing avalanches that follow power law distributions, many small avalanches, few large ones, no characteristic scale. This scale-free behavior appears throughout nature, earthquake magnitudes, forest fire sizes, extinction events, even wealth distributions and city populations. Why do such different phenomena exhibit similar statistical patterns? Perhaps they represent critical states, systems poised at transitions between order and disorder where fluctuations propagate across all scales. Perhaps evolution drives systems toward criticality, maximizing information processing or adaptability. Or perhaps we notice these patterns selectively, ignoring phenomena that do not follow simple scaling laws. Distinguishing genuine universality from observer bias remains challenging. Self-organization extends to living systems. Slime molds, despite lacking brains or central coordination, solve optimization problems like finding shortest paths through mazes. They aggregate from independent cells into multicellular structures following chemical gradients, demonstrating that intelligence, or at least problem-solving, need not require neurons. Ant colonies exhibit collective intelligence, with simple individuals following local rules producing sophisticated colony-level behaviors, food finding, nest building, warfare, agriculture. No ant understands the colony's strategy, yet the colony succeeds through distributed decision-making. Could consciousness itself be an emergent phenomenon in this sense? Not something fundamental requiring special physics, but a natural consequence of sufficiently complex information processing. Integrated information theory proposes that consciousness corresponds to how much information a system integrates, how much each part depends on others. High integration produces high consciousness. This theory makes testable predictions about which brain states should be conscious and permits, in principle, quantifying consciousness in systems ranging from simple circuits to complex brains to possible artificial intelligences. But emergence raises philosophical puzzles. If higher-level properties arise from lower-level components following simpler rules, do the higher-level properties really exist or are they merely convenient descriptions? Does temperature exist or only molecular motion? Does money exist or only paper and metal and electronic records? Does consciousness exist or only neural firing patterns? This is the problem of reduction. At what point does a collection of parts become a new thing with properties not possessed by components individually? A pile of sand adds one grain at a time. At what point does it become a heap? There is no sharp boundary, yet we recognize heaps when we see them. This vagueness seems fundamental rather than merely linguistic. Reality itself might contain inherent fuzziness, categories bleeding into each other, properties existing in degrees rather than absolutes. Classical logic struggles with such gradations, preferring sharp true or false distinctions. Fuzzy logic and quantum superposition suggest nature disagrees. Speaking of quantum effects, they may penetrate deeper into biology than once thought. Photosynthesis achieves remarkable efficiency converting light into chemical energy, approaching theoretical limits. How? Quantum coherence appears crucial. Excitations propagate through molecular complexes as quantum waves. Sampling multiple pathways simultaneously and selecting optimal routes. This quantum biology operates at room temperature in wet noisy environments, conditions thought to destroy delicate quantum states rapidly. Yet evolution found ways to exploit quantum effects for practical advantage. Birds navigate using magnetic fields, detecting directions with precision that seems impossible using classical physics. Proteins in their eyes contain radical pairs, molecular fragments with unpaired electrons, whose quantum states are sensitive to magnetic field orientation. Quantum entanglement between electrons might provide directional information, though details remain debated. If true, bird brains process quantum information as part of routine sensory perception. Even our sense of smell might involve quantum effects. The standard model of olfaction suggests receptors recognize molecular shapes, like keys fitting locks. But molecules with similar shapes sometimes smell different while molecules with different shapes smell similar. An alternative theory proposes that receptors detect molecular vibrations through quantum tunneling. Electrons jump between states with probabilities depending on vibrational frequencies. This would explain otherwise puzzling observations, though experimental tests yield mixed results. Whether quantum effects are truly necessary for these biological functions or merely incidental remains uncertain. But the possibility that life exploits quantum mechanics for evolutionary advantage suggests a deep connection between the quantum and classical worlds that our current theories inadequately capture. We tend to treat quantum mechanics as relevant only at small scales and low temperatures, classical physics governing everything else. Biology hints that the boundary is more permeable, that quantum and classical are not separate realms but interwoven aspects of a single reality we do not yet fully comprehend. Returning to fundamental physics, symmetry plays a curious role. Physical laws exhibit symmetries, invariances under transformations that leave essential features unchanged. Rotate your experiment and the results remain identical, indicating rotational symmetry. Shift it in time or space and outcomes do not change, reflecting temporal and spatial homogeneity. These symmetries connect directly to conservation laws through Noether's theorem. Time invariance implies energy conservation, space invariance implies momentum conservation, rotational invariance implies angular momentum conservation. But nature also exhibits broken symmetries. The early universe was symmetric, with all forces unified and particles indistinguishable. As it cooled, symmetries spontaneously broke, differentiating forces and particles, like water freezing into ice with crystal structures selecting particular orientations from many equivalent possibilities. These phase transitions determine the physics we experience. Had different symmetries broken, the universe would look entirely different. Could further phase transitions await at temperatures and densities we have not explored? Might vacuum itself exist in metastable state, capable of transitioning to lower energy configurations? If so, a bubble of true vacuum could nucleate somewhere in space and expand at light speed, converting everything it touched into new physics with different constants and forces. This vacuum decay would erase the universe as we know it, replacing it with something completely different, potentially incompatible with any form of complexity or life. Some calculations suggest our vacuum might indeed be metastable, but decay rates are so slow that no bubble should form during the entire future history of the observable universe. Probably. We cannot be certain. The landscape of possible physics might be vast, but we inhabit only one valley, one local minimum in some space of possibilities. Whether other valleys exist, whether transitions between them can occur, whether our valley is special in any way, these remain open questions. We are learning the physics of what is, but we barely understand the physics of what could be. And threading through all these mysteries runs mathematics. The language in which natural laws are written. Why does mathematics work? Why should abstract patterns invented by human minds describe physical reality with such uncanny accuracy? Eugene Wigner called this, the unreasonable effectiveness of mathematics in the natural sciences, noting that mathematical structures devised for purely aesthetic or logical reasons often turn out to describe actual phenomena. Non-Euclidean geometry, developed as intellectual exercise exploring what happens if parallel lines do meet, became essential for general relativity. Group theory, abstract algebra studying symmetries, proved central to particle physics. Riemannian geometry, complex analysis, differential equations, tools created by mathematicians for internal reasons became indispensable for physicists describing nature. Either reality is mathematical, built from numbers and relationships, or our brains are somehow tuned to discover mathematical structures that happen to match physical ones, or we notice only those aspects of reality that fit mathematical descriptions while ignoring the rest. Perhaps all three factors contribute. But the effectiveness remains striking. We write symbols on paper following formal rules, derive consequences, then find those consequences reflected in experimental results with precision exceeding many decimal places. The universe appears to obey rules we can express mathematically, rules elegant enough to write on T-shirts yet powerful enough to predict phenomena across scales from subatomic to cosmic. This suggests either that mind and matter share common mathematical foundations, or that evolution shaped our cognition to recognize mathematical patterns because ancestors who saw such patterns survived better, or that mathematical structures possess some form of reality transcending physical implementation. Platonism, the view that mathematical objects exist independently in some abstract realm, appeals to many mathematicians who feel they discover rather than invent mathematics. But how does an immaterial realm of pure form interact with the material world of matter and energy? This is the ancient mystery of universals updated for modern science. And what of consciousness encountering mathematics? When you understand a proof, grasp a theorem, perceive the beauty in an equation, what is happening? Information transfers from symbols to neural activity, yes, but understanding feels like more than mere information processing. There is an aha moment, a gestalt shift where disconnected pieces suddenly cohere into unified insight. Can this be reduced to computation, or does understanding require something computation cannot capture? Roger Penrose famously argued that human mathematical insight cannot be algorithmic, that Gödel's incompleteness theorems show limitations of formal systems that human mathematicians somehow transcend. His argument remains controversial, with critics noting that humans also have limitations and make mistakes, that we might be sophisticated algorithms without realizing it. But the question persists, is mind fundamentally different from machine, or merely more complex? As artificial intelligence advances, this question gains practical urgency. Current AI systems achieve remarkable feats, playing games at superhuman level, generating convincing text, recognizing images, translating languages, yet seem to lack genuine understanding. They are pattern matchers, statistical engines processing vast data to find correlations and make predictions. When an AI generates a sentence or plays a move, is it understanding or merely manipulating symbols according to learned rules? Can you have intelligence without understanding? Can you have understanding without consciousness? These philosophical puzzles become scientific ones as we build systems that challenge our intuitions about mind, intelligence, and awareness. If we create an artificial mind that claims to be conscious, that passes every behavioral test for consciousness, how do we verify the claim? The philosophical zombie problem, the hypothetical of a being physically identical to a human but lacking inner experience, becomes practically relevant. We cannot peer inside to check for consciousness. We must infer it from behavior and structure. But what behaviors or structures are sufficient? This is the hard problem again, approached from engineering rather than neuroscience. Perhaps consciousness is not binary but graded, existing in degrees across different systems. Perhaps there is something it is like to be a thermostat, albeit vastly simpler than what it is like to be human. Perhaps consciousness pervades nature, present wherever information is integrated, with complexity determining richness of experience rather than existence of experience. This panpsychism, the view that mind is fundamental and ubiquitous, was ancient philosophy now reappearing in modern dress, supported by some neuroscientists and philosophers though rejected by others as unnecessary multiplication of mysteries. And mysteries multiply whenever we examine carefully. The placebo effect demonstrates that belief affects physiology through mechanisms poorly understood. Patients improve when given inert substances they believe are medicine. This is not mere imagination, measurable physiological changes occur, pain reduces, immune responses strengthen, symptoms genuinely diminish. How does expectation translate into biological reality? What neural pathways mediate between thought and healing? Can we harness this therapeutically, using mind to influence body more effectively? Meditation, hypnosis, biofeedback hint at possibilities. The boundary between psychological and physical proves less sharp than assumed. Similarly, the observer effect in quantum mechanics continues generating philosophical perplexity despite practical understanding. Measurement collapses wave functions, transforming quantum possibility into classical actuality. But what constitutes measurement? Does it require conscious observers or merely interactions with macroscopic systems? Does observation create reality or merely reveal pre-existing states? Different interpretations answer differently, yet experiments cannot distinguish between them. Perhaps they are all correct descriptions from different perspectives, or perhaps some future insight will identify the right interpretation and explain why others seemed plausible. Everywhere we probe deeply, foundations become uncertain. Not because knowledge is impossible but because reality resists simple categorization. Particle or wave? Both and neither. Determined or random? Depends on context. Observable or hidden? Depends on scale and interaction. These dualities and ambiguities are not failures of description but accurate reflections of how nature actually operates. Reality is more subtle than everyday experience suggests, requiring multiple complementary descriptions rather than single unified accounts. And perhaps this is the deepest discovery of all, that the universe is comprehensible but not simply so, knowable but not exhaustively, describable but not uniquely. We can understand without understanding completely. We can know without knowing everything. We can describe without describing perfectly. The quest for knowledge continues not toward a final endpoint where all questions are answered but toward ever deeper appreciation of profound richness, endless complexity, and infinite subtlety woven into the fabric of existence itself. So yes, emphatically yes, there remains so much more to discover that claiming otherwise would be not just premature but absurd. We stand at the beginning of understanding, not the end. What we have learned barely scratches the surface of what awaits. The universe extends before us, vast and strange and beautiful, filled with wonders we have yet to encounter, truths we have yet to uncover, mysteries we have yet to perceive. Even our own planet harbors secrets that would astonish those who assume Earth is fully mapped and understood. Beneath the ocean surface, covering 70% of our world, lies terrain more alien than Mars. We have better maps of the Martian surface than of our own seafloor. The abyssal plains, mid-ocean ridges, and deep trenches remain largely unexplored, visited by humans far less frequently than space. Down there in perpetual darkness, under crushing pressures that would compact steel, entire ecosystems thrive around hydrothermal vents, volcanic chimneys spewing superheated mineral-rich water into frigid seas. These vent communities survive without sunlight, the fundamental energy source for nearly all surface life. Instead, bacteria harvest chemical energy from hydrogen sulfide and methane, converting toxic compounds into organic matter through chemosynthesis rather than photosynthesis. Giant tube worms, eyeless shrimp, white crabs cluster around black smokers in densities rivaling tropical reefs, all fed ultimately by Earth's internal heat rather than solar radiation. This demonstrates that life need not depend on stars, that biology can tap alternative energy sources, that habitable zones might extend far beyond our previous assumptions. If life thrives in Earth's lightless depths, why not in the subsurface oceans of Europa or Enceladus, beneath kilometers of ice, warmed by tidal flexing rather than sunlight? And the deep ocean continues yielding surprises. Bioluminescence, biological light production, proves far more common in the depths than on the surface. Creatures generate their own illumination through chemical reactions, creating flashes to attract mates, lures to trap prey, camouflage to match the faint light filtering from above. Some emit red light that most deep-sea creatures cannot perceive, creating private communication channels invisible to predators and prey alike. This represents biological cryptography, encoded signals that only intended recipients can decode. Giant squids, creatures of legend for centuries, were finally photographed alive in their natural habitat only in 2004, and filmed in 2012. These animals grow to tremendous sizes, 40 feet or more, yet remain so elusive that we know almost nothing about their behavior, reproduction, or population. What else lurks in the deep? How many large species remain undiscovered? Sonar occasionally detects unidentified sounds, the bloop, the Julia, the train, acoustic phenomena that might represent unknown animals, geological processes, or artifacts of sound propagation through complex ocean layers. The sea keeps its secrets well. Beneath the seafloor itself, life extends kilometers into Earth's crust. Microbes inhabit pore spaces in rocks, metabolizing so slowly that individual cells might divide once per century or less. These deep biosphere organisms might account for a significant fraction of Earth's total biomass, an entire shadow biosphere living beneath our feet, inaccessible except through expensive drilling operations. How deep does life extend? What are the temperature and pressure limits? Do subsurface microbes exchange genetic material with surface organisms, or do they represent isolated evolutionary experiments running in parallel for billions of years? And speaking of Earth's interior, we understand surprisingly little about what lies beneath our feet. The deepest hole ever drilled, the Kola superdeep borehole in Russia, reached just 12 kilometers, barely scratching the crust. The mantle, comprising most of Earth's volume, remains inaccessible to direct sampling. We infer its composition from seismic waves, from material brought up by volcanoes, from meteorites that presumably resemble primordial Earth. But we cannot directly observe the mantle structure, dynamics, or detailed composition. We do not know precisely how convection operates there, how plumes form and rise to create hotspots like Hawaii, how slabs of oceanic crust sink and are recycled. The core itself presents even deeper mysteries. We know it is primarily iron, liquid on the outside, solid at the center despite higher temperatures because of immense pressure. The liquid outer core generates Earth's magnetic field through a dynamo process involving convection, rotation, and electrical currents. But the details remain unclear. Why does the field occasionally reverse, north becoming south and vice versa? These reversals happen irregularly, sometimes after a few 100,000 years, sometimes after tens of millions. During reversals, the field weakens, potentially exposing the surface to increased cosmic radiation. What triggers these flips? Can we predict them? Is Earth overdue for a reversal given that the last one occurred 780,000 years ago? The solid inner core, that sphere of crystallized iron at Earth's center, appears to rotate slightly faster than the rest of the planet. This superrotation, just fractions of a degree per year, was discovered only recently and remains poorly explained. The inner core may also have its own core, an innermost inner core with different crystal structure, suggested by how seismic waves travel through it. But confirming this requires more earthquakes in the right locations generating waves that pass through the center at useful angles. We wait for the planet to reveal its heart through violent shaking. Meanwhile, above ground, the atmosphere holds puzzles of its own. Weather remains only partially predictable despite enormous computational resources dedicated to forecasting. The equations governing fluid flow are deterministic yet chaotic, sensitive to initial conditions in ways that limit prediction horizons. Edward Lorenz discovered this accidentally when running weather simulations. Tiny rounding errors in initial conditions produced wildly different outcomes, demonstrating that long-range weather prediction faces fundamental rather than merely practical limitations. This is the butterfly effect. A butterfly flapping wings in Brazil might theoretically alter tornado formation in Texas weeks later, not because butterflies directly cause tornadoes but because atmospheric dynamics amplify tiny perturbations unpredictably. Yet some aspects of weather follow predictable patterns. Seasonal cycles, climate zones, prevailing winds obey regular principles. The boundary between predictable and unpredictable, between orderly and chaotic, runs through the atmosphere in complex ways we are still mapping. Climate differs from weather, long-term averages and trends versus day-to-day variations, but predicting climate change involves similar challenges. Models must simulate not just atmosphere but oceans, ice sheets, vegetation, carbon cycles, all interacting through feedbacks that can amplify or dampen perturbations. Small errors in understanding these feedbacks produce large uncertainties in predictions. And climate history reveals surprises. Earth has been far warmer and far colder than today. Ice ages and hothouse epochs alternate through geological time for reasons still debated. Variations in Earth's orbit, Milankovitch cycles, modulate solar heating and apparently trigger ice ages, but the orbital changes seem too subtle to explain the dramatic climate swings observed. Feedbacks must amplify the astronomical signal. Ice reflects sunlight, cooling further, carbon dioxide dissolves in cold oceans, removing greenhouse gases, cooling more, vegetation changes alter albedo and carbon storage. These feedbacks can trigger tipping points where climate shifts abruptly from one stable state to another. The Younger Dryas event demonstrates this dramatically. About 12,000 years ago, Earth was warming from the last ice age when suddenly temperatures plunged back to near glacial conditions for over a millennium before warming resumed. What caused this? The prevailing theory involves meltwater from retreating ice sheets disrupting ocean circulation, shutting down the Gulf Stream and plunging the North Atlantic region back into cold. But details remain uncertain and alternative explanations, meteor impacts, volcanic eruptions, continue being proposed. Looking deeper into Earth's climate past reveals even stranger epochs. The Cryogenian period, roughly 700 million years ago, apparently saw Earth completely frozen, snowball Earth, where glaciers extended to the equator and oceans iced over entirely or nearly so. How did life survive? How did Earth escape this frozen state? Volcanic outgassing continued beneath the ice, gradually accumulating carbon dioxide in the atmosphere without plant life to remove it. Eventually, extreme greenhouse warming melted the ice catastrophically, swinging climate from one extreme to another. Evidence for snowball Earth is strong but not unanimous. Some geologists favor slushball scenarios with open water near the equator, and explaining how photosynthetic organisms survived remains challenging. Even further back, the faint young sun paradox puzzles planetary scientists. 4 billion years ago, the sun was roughly 30% dimmer than today. Earth should have been frozen solid. Yet geological evidence indicates liquid water existed, abundant enough to create the sedimentary rocks we find from that era. Something kept Earth warm despite the dim sun-enhanced greenhouse effect from more atmospheric carbon dioxide. Different atmospheric composition with more methane. Clouds that trapped heat more effectively. We do not know, and this uncertainty complicates understanding of early Earth conditions when life originated. The very concept of time's arrow connects to these questions of order and disorder, pattern and chaos. Entropy provides one explanation: time points toward increasing disorder, but this merely restates the observation rather than explaining it. Why did the universe start in an extremely low entropy state? The Big Bang could have produced maximum entropy immediately, a featureless soup of radiation. Instead, it produced a highly ordered state that has been evolving toward disorder ever since, creating temporary pockets of complexity, stars, planets, life, through local decreases in entropy paid for by larger increases elsewhere. Gravity plays a peculiar role in entropy's story. Gravitating systems have negative heat capacity, adding energy makes them cooler, removing energy makes them hotter. A star that radiates energy contracts and heats up rather than cooling down, counter to intuition. This means gravitational systems can spontaneously form structure, clumping together and creating order even as entropy increases. Black holes represent the ultimate endpoint, maximum entropy for a given mass, surface area determining information content according to the holographic principle. The universe's entropy budget is dominated by black holes, everything else contributes negligibly. But this raises questions about information and reality. If a black hole's information content is proportional to its surface area rather than its volume, does this mean the three-dimensional interior is somehow encoded on the two-dimensional